So in this video, I'm going to solve some MCQ questions on simple harmonic motion. I'll start with this question where we have a relaxed spring that protrudes from an opening 0.05 meters as shown in figure A. A 1 kilogram block is found to just force the spring completely into the opening as shown in figure B. We want to find the spring constant K, so we can look at figure B, in which we see that the spring is now compressed and is thus exerting some restoring force. And this force will be acting on this block in addition to the weight of the block itself. So we can use actually Newton's first law acting on the block in order to study for the spring constant. So on this block we have the spring force and the weight. Any force which is downwards we consider it to be negative because these are vectors. So to resolve vectors we need to project. Here I'm projecting along the vertical direction. Any force which is upward, I will take it to be positive, and any force which is downward, I will take it to be negative. So this gives me the following scalar equation, and I obtain that the weight is equal to the spring force. So M times G equals K times X. I no longer put the negative sign because I am now dealing with the scalar quantities. I want to solve for K. So this will be mg over x. M is 1 kilograms, G is 9.8, and X is 0.05 meters. So we solve this, we obtain 196 newtons per meter for the spring constant. Now, in the next question, we want to find the potential energy stored in the spring in figure B. The potential energy stored in the spring, this is the elastic potential energy, and this is equal to half kx squared. The spring constant, we found it in the previous part, it is 196 newtons per meters, and x is given to be 0.05 squared, so we can solve for the energy stored in the spring. In the next question, we have a spring in a special cannon. The spring has a stiffness of 1,800 newtons per meters. In cocking the cannon, the spring is compressed 0.55 meters. We want the initial speed of a 7 kilogram cannonball at rest on the free end of the spring when it is released. So this cannon has a spring which was compressed by 0.55 meters. So, and once it released, it basically pushes on a cannonball. So we want the speed of this cannonball once the spring is released. In that case, basically, the speed of the cannonball is acquired from the elastic potential energy that the spring has. And namely, we can find this by equating the energies, the initial energy when the spring is compressed to the final energy when the spring is released. Now, of course, we don't have any changes in height here, so the energy will namely be only the elastic potential energy and the kinetic energy. The initial speed of the cannonball is 0 because it was at rest, so this cancels out. And once it is released, the spring is gonna be at its natural length, so it will not have any stored elastic potential energy anymore. So we can just substitute now for the equations, and we can solve for the speed of the cannonball. So the speed can be written as kx squared over m with a radical. So this will be radical 1800 newtons per meter times the compression, which is 0.55. This is squared divided by the mass, which is 7 kilograms, and this gives us 8.8 meters per second. Notice that if you forget to apply the radical, you actually obtain a value of 77 meters per second, and you might end up choosing answer A, which is a bit tricky. In this question, we have a spring with a spring constant K equals 1600 newtons per meter. It is at rest on the bottom of an inclined plane. A 7 kilogram block slides down the plane and makes contact with the spring at point A as shown. After contact, the spring is compressed to point B, 0.2 meters from point A, where the speed of the block is 0. What was the speed of the block just before contact with the spring? So here just remember that we have like some different scenarios or different parts of the motion. The block was released from some height, not sure how much this height is, and then it reaches point A. Point A is basically here. So the block reaches point A, which is here, and it reaches A with some non-zero speed, not sure how much that is, but the spring is not yet compressed, and then the block compresses the spring. So in that case, our block becomes compressed, and now we are at the maximum compression point, which is at B. So between A and B, there is some given distance. We are given that this distance is 0.2 meters, and this point is the maximum compression. So x at B is x maximum, or the amplitude of the compression in this case, and the speed of the block reaches 0 at this point. Our question is, we want to find the speed of the block just before contact with the spring. So this is basically the speed at point A, because this is the point where the block starts touching the spring. It's at this point here in this case, and we still haven't compressed the spring. And then the spring compresses. As it compresses, the block slows down until it reaches a speed of 0 when it reaches point B, and it completely stops. So to find this speed, we will again solve for the conservation of energy. I will say that the energy at A equals the energy at B. Now, one important thing to notice is that between A and B, the height is changing. So we basically have to account for gravitational potential energy. So when I substitute for the energies, I will write U gravitational at A, and the elastic potential energy at A, and the kinetic energy at A. I will equate these to the gravitational potential energy at B, plus the elastic potential energy at B, plus the kinetic energy at B. Now we can simplify and cancel out quantities which we know are 0. X at A is 0, so the elastic potential energy at A cancels out. X at B is non-zero. V at B is 0, so I can cancel out the kinetic energy at B. Now I'm gonna substitute by the formulas. I have mg HA plus half m VA squared equals mg HB plus half kxb squared. So, well, if we look at what we should substitute, this is the quantity we want, the speed at A. We have the mass, 7 kilograms. We don't have the height at A or the height at B. We do have the compression xb because it's the same as the distance covered by the block right here. So this is the same as the distance covered, which is 0.2 meters. Now we are given this angle here, and we can thus make use of it in order to find the heights at A and B. Now, we will not be able to find the height at A itself because we will essentially need this whole distance, which we don't know. Instead, I'm gonna find the difference between HA and HB, which is gonna be none other but, so if we subtract these two heights, this is HA, this is HB, if we subtract them, we get this quantity. And if the angle here is 55, sine 55 is gonna be equal to HA minus HB over the hypotenuse, which is none other but the distance covered, which is 0.2 meters. So I just found a numerical value for HA minus HB. What I can do is that in my equation, I'll take HB to the other side so that I can put HA minus HB together. So if we actually rearrange this equation for VA, we will obtain VA to be equal to mg. Actually, I write it as minus mg HA minus HB plus half kxb squared, and I will multiply this by 2 over m and put a radical to find V at A. So as we just proved, we're gonna write, instead of HA minus HB, I'll write what we got here, which is 0.2 sine 55. And the rest will basically be just some substitution. The mass is 7 kilograms. Pay attention, the mass here and here, they do not cancel out because I have a plus sign here. The spring constant was given 1,600. So this gives us an answer of 2.4 meters per second.